Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year is 1930. A profound unease permeates the foundations of mathematics. Russell's paradox, a seemingly simple yet devastating logical contradiction, had shaken the very core of set theory, a cornerstone of mathematical reasoning. The ambition to build a completely rigorous and consistent formal system for all of mathematics, a project championed by David Hilbert, faced a formidable challenge. This quest for absolute certainty, a Hilbert program, aimed to establish mathematics on an unshakable logical foundation, free from paradox and contradiction. A shadow of uncertainty hung over this audacious endeavor. Alonzo Church, a young mathematician whose keen intellect and unwavering dedication would play a pivotal role in navigating this turbulent intellectual landscape, entered the scene. Church's contributions extend far beyond resolving a single puzzle. His work fundamentally reshaped our understanding of computation and the limits of formal systems. He tackled the central problem of the time. A precise, universally accepted definition of effective computability remained elusive. The concept itself, intuitively grasped by mathematicians, lacked a formal, rigorous expression. How could one definitively capture the essence of what a machine, or a human for that matter, could effectively compute? This was a crucial question that demanded an answer. Church's initial foray into this uncharted territory involved the creation of Lambda Calculus, a system of symbolic logic that would prove remarkably prescient. Lambda Calculus, at its core, provided a novel way to represent functions and their application. This elegant formalism initially met with a degree of skepticism. Its abstract nature and unfamiliar notation hindered immediate comprehension. Beneath this initially challenging exterior resided a powerful tool, one that would revolutionize our understanding of computation. This essay undertakes a detailed exploration of Church's profound influence on the development of computer science and mathematical logic. We will examine the intellectual climate that shaped his work, delving into the intricacies of the Hilbert program and the groundbreaking discoveries of Gödel. We will trace the evolution of Church's ideas, from the initial development of Lambda Calculus to his formulation of the Church-Turing Thesis, a cornerstone of modern computation theory. We will explore the lasting impact of his contributions, highlighting their enduring relevance in contemporary computer science and mathematical foundations. We will consider the broader philosophical implications of Church's work, reflecting on the limitations of formal systems and the enduring quest for a complete understanding of computation. The journey begins with a closer examination of the intellectual landscape of the early 20th century. The Hilbert program, with its ambitious goal of providing a complete and consistent axiomatic foundation for all of mathematics, provided the fertile ground upon which Church's work would flourish. Hilbert's vision faced a significant obstacle in the form of Gödel's incompleteness theorems. These theorems, published in 1931, demonstrated the inherent limitations of formal systems, revealing the existence of true statements within a formal system that could be proven within that system. This discovery dealt a significant blow to the Hilbert program, raising fundamental questions about the completeness and consistency of formal mathematical systems. Gödel's work, while highlighting the limitations of formal systems, simultaneously underscored the need for clear and unambiguous definition of effective computability. If one could prove every true statement within a formal system, one needed a precise way to define what could be effectively computed, what could be determined through a mechanical, algorithmic process. Prior to Church's contributions, various attempts had been made to formalize the notion of effective computability. Program and Gödel, mathematicians, had made significant strides in this direction. Their efforts possessed less elegance and generality than Church's Lambda Calculus would soon provide. The stage was set for a new approach, a method that would capture the essence of computation in a rigorous and comprehensive manner. Church's work takes center stage here, offering a novel and profoundly influential solution to a problem that had baffled mathematicians for years. The following sections will explore the details of Lambda Calculus and its profound consequences in greater depth, revealing the genesis of a revolution in the world of computation and logic. The quest for rigorous foundation for mathematics, a pursuit that had captivated thinkers for centuries, reached a fever pitch in the early 20th century. David Hilbert, a towering figure in the mathematical landscape, articulated a vision, a grand program intended to secure the edifice of mathematics against the perceived threat of paradoxes and inconsistencies. This vision, known as the Hilbert program, aimed to formalize all of mathematics within a single, comprehensive axiomatic system. The hope existed that by expressing mathematical truths as formal statements within this system, and by providing a mechanical procedure to prove these statements, the consistency and completeness of mathematics could be definitively established. Hilbert envisioned a system where every mathematical statement could be expressed in a precise symbolic language, and where proofs could be carried out according to a set of explicit rules, essentially reducing mathematical reasoning to a form of calculation. This would eliminate ambiguity and provide a clear and verifiable method for determining the validity of any mathematical claim. The ambition was audacious to create a mathematical utopia free from doubt and contradiction. The Hilbert program resonated deeply within the mathematical community, inspiring a generation of researchers to pursue its ambitious goals. Formal systems were developed, logical calculi were refined, and significant progress was made in formalizing various branches of mathematics. This optimistic trajectory soon encountered a formidable obstacle, a challenge that would ultimately shatter the dream of a complete and consistent formalization of all of mathematics. That challenge appeared as Gödel's incompleteness theorems, published in 1931. These theorems, arguably among the most profound results in the history of logic and mathematics, demonstrated inherent limitations in any formal system capable of expressing basic arithmetic. Gödel's first incompleteness theorem states that within any such system, there will always exist statements that are true, yet cannot be proven within the system itself. In other words, there are mathematical truths that lie beyond the reach of formal proof. Gödel's second incompleteness theorem extends this result, demonstrating that no consistent formal system can prove its own consistency. This meant that the Hilbert Program's goal of providing a formal proof of the consistency of mathematics was fundamentally unattainable. The impact of Gödel's theorems was seismic, shaking the foundations of mathematical certainty and forcing a reevaluation of the very nature of mathematical knowledge. The incompleteness theorems revealed the limits of formalization, while also affirming its importance. They highlighted the crucial role of human intuition and ingenuity in mathematical discovery. Mathematics could be reduced to a purely mechanical process only to a degree. Understanding required something more. The implications of Gödel's work extended far beyond the realm of pure mathematics. They touched upon fundamental questions about the nature of knowledge, the limits of computation, and the relationship between mind and machine. If formal systems, even those designed to capture the essence of mathematical reasoning, were inherently incomplete, what did this say about the possibility of creating truly intelligent machines or fully understanding the human mind through purely computational models? Gödel's incompleteness results immediately necessitated a clarification of the concept of effective calculability. The Hilbert program depended on the idea that proofs could be performed by a mechanical procedure, an algorithm executable without ingenuity or insight. The notion of a mechanical procedure remained somewhat vague and intuitive. Gödel's work highlighted the importance of a precise, formal definition of what it means for a function or a process to be effectively calculable. The question arose, could one rigorously and unambiguously define the set of all functions computable by a mechanical process, by an algorithm? This question held profound implications for the foundations of mathematics in the emerging field of computer science. A formal definition of effective calculability would provide a benchmark for comparing different computational models. It would allow mathematicians and logicians to explore the limits of computation to determine which problems could be solved algorithmically and which problems would remain beyond the reach of mechanical computation. The challenge of defining effective calculability attracted the attention of many brilliant minds. Prior to Church's groundbreaking work, several attempts aimed to capture this elusive concept in a formal framework. One notable approach involved the development of recursive functions, pioneered by Gödel along with Jack Herbrand. The Herbrand-Gödel definition of recursive functions provided a powerful tool for expressing a wide range of computable functions. It involved defining a class of functions by starting with a set of basic functions, such as the zero function, the successor function, and projection functions, and then specifying a set of rules for constructing more complex functions from these basic building blocks. These rules included composition, recursion, and minimization. The Herbrand-Gödel definition was successful in capturing many intuitively computable functions, yet it possessed certain limitations. Its formalism proved cumbersome, enduring both practical application and logical analysis. The question remained whether recursive functions fully captured the scope of effective calculability, or if mechanical processes could compute functions beyond the Herbrand-Gödel framework's expressive capacity. The mathematical community sought a more refined, broadly applicable, and convincing definition of effective calculability, a formalism capable of expressing a diverse set of computable functions, while also facilitating mathematical analysis and proof, was desired. Alonzo Church then introduced the Lambda Calculus, a revolutionary concept. His work delivered an innovative and deeply impactful solution to a long-standing challenge for mathematicians and logicians. Alonzo Church's response to the search for a definitive formalization of effective computation was the Lambda Calculus, an innovative system. Developed in the 1930s, this calculus presented a fundamentally different method for defining functions and computation compared to the increasingly prominent recursive functions. It served as a comprehensive framework for expressing any process executable through purely mechanical means. The Lambda Calculus is fundamentally a formal system for function manipulation. Within the Lambda Calculus, everything, including data, is a function. This approach enables a remarkably consistent and potent method for representing computation. The Lambda Calculus possesses a surprisingly simple syntax, constructed from only three expression types: variables, function abstractions, and applications. A variable, typically represented by a single letter such as x, y, or z, signifies an unknown or unspecified value. A function abstraction, written as lambda followed by a variable, and then an expression, defines a function accepting a single argument. For instance, lambda x.x signifies the identity function, a function returning its argument unchanged. The dot separates the bound variable from the expression defining the function's behavior. Application represents the act of applying a function to an argument. It is written by placing the function and its argument side by side, enclosed in parentheses. For example, open parenthesis lambda x.x close parenthesis y represents the application of the identity function to the variable y, which would then reduce to y itself. The Lambda calculus derives its power from its reduction rules, which govern how expressions are simplified or evaluated. There are three primary reduction rules: alpha conversion, beta reduction, and eta conversion. Alpha conversion, also known as alpha renaming, allows a change to the name of a bound variable within a function abstraction. The expression's meaning remains unchanged, provided the new variable name does conflict with any other variable names in the expression. For example, lambda x.x can be alpha converted to lambda y.y without altering the function's behavior. This rule is essential for avoiding variable capture during beta reduction. Beta reduction constitutes the core of the Lambda calculus, formalizing the process of function application. It states that when a function abstraction is applied to an argument, the argument is substituted for all free occurrences of the bound variable within the function's body. A free occurrence of a variable is one that is bound by a lambda abstraction within the expression. For example, the expression open parenthesis lambda x.x plus 1 close parenthesis 2, where plus 1 is some previously defined function representing addition by 1, would beta reduce to 2 plus 1. Eta conversion expresses the concept of extensionality. Two functions are equivalent if they produce the same output for all inputs. It states that lambda x.fx is equivalent to f, provided that x does occur free in f. In other words, if a function takes an argument and applies another function to it, it can be simplified to the original function. For instance, lambda x dot open parenthesis plus 1 close parenthesis x is equivalent to plus 1. These three simple rules, alpha conversion, beta reduction, and eta conversion, provide the foundation for all computation within the Lambda calculus. Functions can be defined, applied, and simplified using these rules, allowing for the expression of complex algorithms and data structures. To illustrate the expressive power of the Lambda calculus, consider how one might represent basic arithmetic. The Lambda calculus deals exclusively with functions, and numbers can be encoded as functions that represent how many times another function is applied. These encodings are known as Church numerals. The Church numeral 0 is defined as lambda f dot lambda x dot x. The Church numeral 1 is defined as lambda f dot lambda x dot f open parenthesis x close parenthesis. The Church numeral 2 is defined as lambda f dot lambda x dot f open parenthesis x close parenthesis, and so on. Each Church numeral represents a function that takes two arguments, a function f and a value x, and applies f to x a certain number of times. Addition can also be defined as a Lambda calculus expression. The addition function takes two Church numerals as arguments and returns their sum. Also as a Church numeral, the addition function is defined as lambda m dot lambda n dot lambda f dot lambda x dot mf open parenthesis and fx close parenthesis. This function applies the function f m times starting with open parenthesis and fx close parenthesis, effectively applying f a total of m plus n times. Arithmetic operations, logical operations, and data structures can be encoded within the Lambda calculus. This demonstrates its ability to represent a wide range of computational concepts. Church's aim in developing the Lambda calculus was to create a universal system for expressing any effective computation. He sought to provide a rigorous and unambiguous definition of what it means for a function to be computable. The Lambda calculus, with its simple syntax and powerful reduction rules, appeared to be a promising candidate. It offered a clean and elegant formalism that avoided the complexities and ambiguities of natural language. Proving the universality of the Lambda calculus proved to be a significant challenge. Demonstrating definitively that every effectively calculable function could be expressed within this framework was difficult. Some functions, computable by other means, might lie outside the reach of the Lambda calculus. This problem was further complicated by the absence of a precise definition of effectively calculable at the time. The notion was intuitive, though it lacked a formal grounding. The Lambda calculus, in its initial conception, had certain limitations. While it could represent a wide range of functions, it also allowed the construction of expressions that did have a normal form, meaning they could be reduced indefinitely without ever reaching a final result. This raised questions about the system's consistency and meaning. The presence of such non-terminating expressions presented a challenge to interpreting the Lambda calculus as a model of computation. The Lambda calculus represented a major step forward in the quest for a formal definition of computability. It provided a novel and influential framework for expressing functions and computations, laying the groundwork for future developments in computer science and mathematical logic. The subsequent formulation of Church's thesis, linking the Lambda calculus to the intuitive notion of effective calculability, further solidified its importance and impact on the field. The Lambda calculus presented a challenge due to certain expressions within the system lacking a normal form, leading to infinite reduction sequences. This raised fundamental questions about the nature of computation and the limits of formal systems. The quest to definitively capture the intuitive concept of effective calculability continued, demanding a more robust and comprehensive framework. From this intellectual ferment emerged one of the most profound and influential statements in the foundations of computer science and mathematical logic, Church's thesis. This assertion, often referred to as the Church-Turing Thesis, posits a fundamental equivalence between the intuitive notion of an effectively calculable function and the formal concept of a function computable by a Turing machine, or equivalently, expressible within the Lambda calculus. To understand the significance of Church's thesis, it is crucial to appreciate the distinction between a thesis and a theorem. A theorem is a statement that can be rigorously proven within a formal system, based on a set of axioms and rules of inference. Church's thesis resides outside the realm of formal proof. It is an assertion about the relationship between a formal system, such as the Lambda Calculus or the Turing machine, and an informal, intuitive concept of effective calculability. Effective calculability describes a process executable by a person adhering to a finite set of instructions, employing pencil and paper in a mechanical manner, demanding no insight or ingenuity. The thesis posits that any function computable via such a mechanical process is also computable by a Turing machine or expressible in the Lambda calculus. Any function computable by a Turing machine or expressible in the Lambda calculus is effectively calculable. A strict mathematical proof is unattainable due to the lack of a formal definition of effective calculability. The thesis relies on substantial evidence and a convergence of independent formalisms. Evidence supporting Church's thesis arises from the equivalent results yielded by numerous attempts to formalize effective calculability using varied approaches. The Lambda calculus, developed by Church, furnishes a formalism. Turing machines, conceived by Alan Turing, offer another. Recursive functions, a class of functions defined by recursion and composition, represent a third. These formalisms, despite their origins and principles, demonstrate equivalent computational power. Each can simulate the others, signifying that any function computable in one formalism is also computable in any of the others. This convergence strengthens Church's thesis. These formalisms appear to have captured the features of effective calculability, indicating a limit to what can be computed by mechanical means. The absence of counterexamples further supports the thesis. Decades of research have yielded no function intuitively effectively calculable yet incomputable by a Turing machine or inexpressible in the Lambda calculus. Church's thesis is an essential concept with profound philosophical implications beyond a technical statement about the equivalence of formal systems. It proposes that the limits of computation are inherent in the nature of effective calculability itself, rather than being arbitrary or dependent on the formalism employed. If Church's thesis is accurate, any process executable by a human following a finite set of instructions is also executable by a machine. This has significant consequences for our understanding of the mind, intelligence, and the limits of automation. The thesis provides a rigorous foundation for the theory of computation, acting as a cornerstone of computer science. It enables computer scientists to reason about the capabilities and limitations of computers in a precise and meaningful manner. It also informs our understanding of the relationship between mind and machine in fields such as cognitive science and artificial intelligence. Church's thesis brilliantly bridges the formal and the informal, the abstract and the intuitive. It offers a powerful framework for understanding the nature and limits of computation, continuing to inspire and challenge researchers in computer science, mathematics, and philosophy. Its enduring influence and the substantial evidence supporting it have solidified its position as a central concept in the foundations of computation, even though it remains a thesis. Its significance extends beyond the technical details of Lambda calculus and Turing machines, addressing fundamental questions about the nature of knowledge, intelligence, and the limits of human understanding. The articulation of Church's thesis provided a profound framework for comprehending computation's essence and its inherent boundaries. Its influence endures, inspiring and challenging researchers across computer science, mathematics, and philosophy. While remaining a thesis, the substantial evidence supporting it has firmly established its position as a cornerstone concept in computational foundations. Its ramifications extend past the technical intricacies of Lambda calculus and Turing machines, touching upon fundamental inquiries into the nature of knowledge, intelligence, and the scope of human understanding. Across the Atlantic, a young British mathematician named Alan Turing was independently grappling with similar questions about the nature of computation and the limits of what could be algorithmically determined. Turing, like Church, sought to formalize the concept of an algorithm, a mechanical procedure that could be carried out without any need for intuition or ingenuity. His efforts led him to conceive of a theoretical device now known as the Turing machine, a deceptively simple yet remarkably powerful model of computation. The development of the Turing machine was driven by a very specific problem, one that had been posed by David Hilbert, a towering figure in mathematics, decades prior. This challenge, known as the Enchanting's problem, or the decision problem, asked whether there exists an algorithm that, given any statement in first-order logic, can determine whether that statement is universally valid, meaning true in all possible interpretations. In simpler terms, Hilbert wanted a mechanical procedure that could automatically decide whether any given mathematical statement was true or false. Turing's genius lay in his ability to break down the abstract problem of computation into a concrete, mechanistic model. The Turing machine consists of an infinitely long tape divided into cells, a read-write head that can move along the tape, and a finite set of states that determine the machine's behavior. The machine operates by reading a symbol from the cell under the read-write head, consulting its current state, and then performing one of three actions: writing a new symbol to the cell, moving the read-write head one cell to the left or right, and transitioning to a new state. This seemingly rudimentary device, Turing demonstrated, was capable of performing any computation that could be carried out by a human being following a fixed set of rules. With his model of computation in hand, Turing turned his attention to the Enchanting's problem. In a landmark paper published in 1936, the same year as Church's publication on Lambda calculus, Turing presented a devastating result. He proved that the Enchanting's problem is without solution. There exists no Turing machine, and therefore no algorithm, that can determine the validity of all statements in first-order logic. This result, independently reached by Church, shattered Hilbert's dream of a mechanical procedure for solving all mathematical problems. Turing's proof, although distinct from Church's, relied on a similar technique of self-reference and diagonalization. He demonstrated that assuming the existence of such a machine leads to a logical contradiction, a paradox that undermines the very assumption itself. The details of Turing's proof are intricate, but the core idea is that a universal Turing machine, one capable of simulating any other Turing machine, could be fed its own description as input. This allows the machine to reason about its own behavior, leading to a situation where it can be forced to contradict itself. Church and Turing, with distinct formalisms, shared a common goal to provide a rigorous definition of computability and to explore its limits. Church used Lambda Calculus, a formal system for expressing functions and computations, and Turing used the Turing machine, a concrete model of a mechanical computing device. Both arrived at the same conclusion that there exist problems that are inherently unsolvable by any algorithmic means. The historical context surrounding these discoveries is crucial to understanding their significance. The 1930s were a time of intense intellectual ferment in mathematics and logic. Gödel's incompleteness theorems, published in 1931, had already shaken the foundations of mathematics by demonstrating that any sufficiently powerful formal system would necessarily contain statements that are true but unprovable within the system itself. Church's and Turing's work built upon Gödel's insights, further revealing the inherent limitations of formal systems and the power of computation. An intriguing aspect of this period is the independent and nearly simultaneous nature of Church's and Turing's discoveries. Both mathematicians, working in different countries and using different approaches, arrived at the same fundamental conclusion about the unsolvability of the shadings problem. This convergence lends further weight to the significance of their results, suggesting that they had tapped into a deep and fundamental truth about the nature of computation. The equivalence of Turing machines and Lambda Calculus, established shortly after their initial discoveries, further solidified the importance of their work. Any computation performable by Turing machine can also be expressed in Lambda Calculus, and conversely. This equivalence demonstrated that these two seemingly disparate formalisms captured the same underlying concept of computability. This equivalence provided strong evidence for the Church-Turing Thesis, which states that any function that is effectively calculable, meaning computable by a human being following a fixed set of rules, can be computed by a Turing machine, or equivalently expressed in Lambda Calculus. The Church-Turing Thesis is a statement about the limits of what can be computed, asserting that the Turing machine and Lambda Calculus capture the full extent of what is algorithmically possible. The Church-Turing Thesis has profound implications for computer science, mathematics, and philosophy. It provides a theoretical foundation for the field of computer science, defining the scope of what computers can and cannot do. It also challenges our understanding of the relationship between mind and machine, raising questions about whether the human mind is itself a kind of computer, subject to the same limitations as Turing machines. The Church-Turing Thesis remains a thesis. Its enduring influence and the weight of evidence supporting it have solidified its place as a central concept in the foundations of computation, profoundly shaping our understanding of the nature of algorithms and their inherent limitations. The assertion that Turing machines and Lambda Calculus capture the full extent of algorithmic possibility has had a transformative effect on the development of computer science. Church's work, initially rooted in logic and mathematics, unexpectedly provided a robust theoretical framework for a field that was then in its nascent stages. Lambda Calculus, in particular, exerted considerable influence on the design and implementation of programming languages. One of the most significant ways in which Church's work impacted computer science is through its direct influence on the creation of functional programming languages. Languages such as Lisp, Scheme, and Haskell owe a considerable debt to Lambda Calculus. Lisp, developed by John McCarthy in the late 1950s, was one of the earliest languages to embrace functional programming principles. The core design drew significant inspiration from the Lambda Calculus, with functions considered first-class citizens. This means they can be passed as arguments to other functions, returned as values from functions, and assigned to variables. This ability to manipulate functions as data reflects the Lambda Calculus's emphasis on function application and abstraction. Scheme, a dialect of Lisp, refined the functional programming paradigm. It adopted a more streamlined and elegant syntax, adhering closely to the principles of Lambda Calculus. Scheme's emphasis on recursion, higher-order functions, and lexical scoping are hallmarks of functional programming, traceable to Church's foundational work. The influence of Lambda Calculus is evident in Scheme's support for continuations, a control flow mechanism that allows programmers to capture the current state of a computation and resume it later. Haskell, a purely functional programming language, embodies the Lambda Calculus in a practical programming language. Haskell's type system, based on the Heinle-Milner type inference algorithm, ensures that all programs are type safe and that functions behave predictably. This strong emphasis on type safety and purity makes Haskell an ideal language for developing reliable and maintainable software. Haskell's support for lazy evaluation, where expressions are evaluated only when their values are needed, is a feature inspired by the Lambda Calculus. Lazy evaluation allows programmers to write more concise and expressive code, avoiding unnecessary computations and improving performance. Church's thesis provided a crucial theoretical foundation for the entire field of computer science. It established a clear boundary between what is computable and what is not computable, defining the limits of what computers can achieve. This understanding is essential for computer scientists as it guides their research and development efforts, helping them to focus on problems that are solvable. The Church-Turing Thesis also has implications for the design of algorithms and the development of computational models. It establishes a standard for evaluating new algorithms and models, confirming their efficiency and power. Church's work on modal logic also gained unexpected relevance in computer science, especially in software verification. Modal logic, concerned with reasoning about necessity and possibility, offers a formal structure for specifying and verifying the behavior of computer systems. Temporal logic, a type of modal logic, is designed for reasoning about time and event sequences. It sees widespread use in computer science for verifying the correctness of concurrent and distributed systems, guaranteeing their intended behavior over time. Temporal logic enables computer scientists to specify properties including safety, liveness, and fairness, which are vital for ensuring the reliability and robustness of software systems. Through the use of temporal logic, computer scientists can formally demonstrate that a system meets its specifications, reducing the need for extensive testing and debugging. The application of modal logic in computer science extends to artificial intelligence, database systems, and network security. In artificial intelligence, modal logic aids in reasoning about the knowledge and beliefs of agents, enabling them to make informed decisions in complex environments. In database systems, modal logic helps specify and enforce integrity constraints, maintaining data consistency and accuracy. In network security, modal logic aids in analyzing security protocols and identifying potential vulnerabilities. Beyond his direct research contributions, Church's role as a teacher and mentor significantly influenced the fields of logic and computer science. He supervised the doctoral work of many students who later made their own significant contributions. Martin Davis, a student of Church, contributed significantly to computability theory and automated theorem proving. Davis's work on Hilbert's 10th problem, which asks whether there is an algorithm for determining whether a given Diophantine equation has a solution, led to its eventual solution, indicating the absence of such an algorithm by Yuri Matijasic, building on work by Davis, Hilary Putnam, and Julia Robinson. This result, known as the Davis-Putnam-Robinson-Matijasic theorem, is a landmark achievement in mathematical logic. Dana Scott, another of Church's students, made fundamental contributions to the development of domain theory, a branch of mathematics that provides a rigorous foundation for denotational semantics. Denotational semantics is a technique for assigning mathematical meanings to programming languages, allowing computer scientists to reason about the behavior of programs in a precise and formal way. Scott's work on domain theory provided the mathematical tools needed to define denotational semantics for a wide range of programming languages, including functional, imperative, and object-oriented languages. His work has had a profound impact on the design and implementation of programming languages, as well as on the development of formal methods for software verification. Through his teaching and mentorship, Church helped to shape the intellectual landscape of logic and computer science, fostering a generation of researchers who continued to build on his foundational work. His influence extends far beyond his own direct contributions, reaching into the work of his students and their students, creating a legacy that continues to inspire and inform researchers today. The impact of Church's work on the development of computer science is undeniable. His Lambda Calculus provided a crucial foundation for functional programming languages, while his thesis defined the limits of what computers can achieve. His work on modal logic found unexpected relevance in software verification, and his role as a teacher and mentor helped to shape the intellectual landscape of the field. Alonzo Church's intellectual journey culminated in a legacy that reshaped the very foundations of logic and computer science. His contributions wove together to form a new understanding of computation, its possibilities, and its inherent limitations. Church's work stands as a testament to the power of abstract thought to eliminate the concrete realities of the digital world. The Lambda Calculus, a formal system initially conceived as a foundation for mathematics, unexpectedly became a cornerstone of computer science. Its elegance rises from its simplicity, a small collection of rules able to express any computation. This economical design reveals its expressive power, a power that continues to echo in the design of modern programming languages. Functional programming languages, with their focus on functions as first-class citizens, have a direct connection to Church's creation. These languages, known for their clarity, conciseness, and fitness for parallel processing, illustrate the lasting practical value of a theoretical construct. The influence of Lambda Calculus reaches beyond the purely functional paradigm, affecting the design of many other languages through features such as anonymous functions and closures. Its impact on the field is widespread, shaping the way programmers consider computation and design software. Church's thesis, another significant contribution, addresses the core question of what it means for a function to be computable. It suggests that any function that is effectively calculable can be computed by a Turing machine or equivalently expressed within the Lambda Calculus. This thesis, While unprovable in a strict mathematical sense, has become a guiding principle in computability theory. It offers a strong and widely accepted definition of computability, enabling researchers to explore the boundaries of what computers can achieve. The implications of Church's thesis are extensive, informing our understanding of the limits of artificial intelligence and the potential for automating complex tasks. It serves as a vital reminder that computation, however powerful, is subject to inherent constraints. The significance of Church's work can be understood by considering a hypothetical scenario, envisioning computer science lacking his contributions. Without the Lambda Calculus, the development of functional programming languages would have been severely hindered, possibly delaying the emergence of key concepts such as higher-order functions and lazy evaluation. The field might have remained largely focused on imperative programming styles, possibly missing the advantages of functional approaches for certain applications. Our understanding of computability benefits greatly from Church's thesis, providing clarity and preventing potential confusion regarding the limits of computation. A universally accepted definition of computability has aided progress in areas such as algorithm, design, and complexity theory. The intellectual landscape of computer science is undoubtedly more developed due to the influence of Church's ideas. Alonzo Church's impact extends to his theorems and formalisms. He cultivated a generation of logicians and computer scientists, instilling a commitment to rigor, clarity, and intellectual curiosity. His students made significant contributions to the field, amplifying his influence. Church's legacy is intertwined with the development of Princeton University as a leading center for logic and computer science research. The intellectual atmosphere he helped create fostered innovation and collaboration, attracting talented researchers from around the world. His role as a teacher and mentor demonstrates his dedication to the advancement of knowledge and the nurturing of future generations of scholars. The elegance of Church's work is notable. He possessed a rare ability to identify the essential features of a problem and to express them in a concise and precise manner. His formalisms, while abstract, are deeply rooted in intuition and provide valuable insights into the nature of computation. The Lambda Calculus captures the essence of function application in a way that is mathematically rigorous and conceptually clear. Church's work demonstrates the power of abstraction to simplify complex problems and to reveal underlying structures. It serves as an inspiration to researchers seeking to develop more elegant and efficient solutions to computational challenges. Church's ideas possess power due to their generality. The Lambda Calculus remains unconstrained by specific hardware or software platforms. It serves as a universal computation model implementable in diverse manners. Church's thesis applies to any conceivable computation model, offering a broad, robust computability definition. The generality inherent in Church's work guarantees its lasting relevance within a rapidly changing technological environment. As new computing paradigms arise, his fundamental insights offer continued guidance and inspiration. Alonzo Church's legacy remains secure. He stands as a foundational figure within the digital age, his ideas shaping computer science's very fabric. His contributions to logic and computability theory continue to resonate with researchers and practitioners. The Lambda Calculus remains a vital tool for understanding and designing programming languages, while Church's thesis provides a crucial framework for exploring computation's limits. His work exemplifies abstract thought's power to transform the world. Alonzo Church's name will forever be associated with computer science's birth as a rigorous, intellectually vibrant discipline, a discipline that continues to profoundly shape our lives. His intellectual offspring, the concepts and the people he influenced, continue to drive innovation and expand the horizons of computational possibility, a fitting tribute to a mind that dared to explore calculation's very essence.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.